Have you ever thought about what happens when, like, you're doing something online and it involves like a bunch of steps, and if one of them messes up, the whole thing just blows up?
Oh, yeah, totally. Like when you're booking a flight and a hotel and renting a car all at once, and you kind of need all of those to go through,
Right.
or you're stuck, right?
Exactly. And the stuff you sent me, it really digs into how these systems, especially databases, make sure that, when a series of actions needs to happen, it either all works or nothing works. It's kind of wild.
It is. And it gets even more complex when you consider that, like, tons of people are using these systems at the same time, all trying to do different things with the same data.
Yeah, without everything just going haywire.
Right. So in this deep dive, we're going to look at the core ideas behind how data integrity is maintained, even with all this simultaneous activity. It's going to be fascinating.
So the sources talk about something called a transaction. What exactly is a transaction in this, like, database world?
Well, a transaction, as your sources describe it, is basically a set of database operations that are treated as one indivisible unit.
Hmm.
Like, it's all or nothing.
Okay, so why is this all or nothing approach so important? Is it just about being tidy, or is there more to it?
Oh, it's way more than tidiness.
Yeah.
It's crucial for maintaining data integrity. Imagine you're transferring money between bank accounts. You don't want the money to disappear from one account and not show up in the other.
All right, that'd be a
A
nightmare.
total nightmare.
Okay.
This all or nothing rule makes sure the database always moves from one valid state to another. If any step in the transaction fails, the whole thing is reversed. It's like baking a cake.
Yep.
You can't just add half the ingredients.
Right. Now, the sources also mention these ACID properties. What do they have to do with databases?
Okay, so ACID stands for Atomicity, Consistency, Isolation, and Durability. These are the four key principles of a reliable transaction. Atomicity is that all or nothing thing we were talking about. Consistency means that the database starts and ends in a valid state following its rules. Isolation means that transactions don't mess with each other when they're happening at the same time. And durability means that once a transaction is done and confirmed, those changes are permanent, even if the system crashes.
Gotcha. So ACID is like the quality seal for a database.
Yeah, exactly. If a system is ACID compliant, you can be pretty confident it's going to handle your data reliably.
The source has this example of transferring $100 between accounts. It uses those SQL commands: begin transaction, update, and commit. Can we break that down and see how those ACID properties come into play?
Sure, let's do it. So begin transaction is like saying, okay, we're starting a transaction now. The update commands are the actual steps in the process. One takes the $100 out of one account, and the other puts it into the second account. Now imagine the second update fails for some reason, like the account number is wrong. Because of atomicity, the entire transaction would be rolled back. So even though the first update worked, the system would undo it as well to keep things consistent. No money magically disappears. Isolation ensures that no one else sees a messed up view of the accounts while this transaction is in progress. And durability ensures that if the transaction completes successfully with commit, that $100 transfer is permanently recorded.
So the takeaway is, if you've got a bunch of actions in the database that are connected, always wrap them in a transaction.
Absolutely. It's like the golden rule of database reliability.
Now, the sources move on to how we actually control these transactions. They mention commands like begin transaction, commit, and rollback. It seems pretty straightforward, but are there any, like, subtle things we should know about?
Yeah, you're right. The basics are pretty clear. Begin transaction starts the transaction. Commit says, we're good, make these changes permanent. And rollback is like, abort, undo everything. I think the trickiest part with rollback is knowing exactly when to use it.
Okay.
It's your main tool for handling errors and making sure that if something goes wrong, you don't end up with a half-finished, messed up database.
Now there's the SAVEPOINT command. Sounds interesting.
Oh yeah, SavePoint is like setting a bookmark in your transaction. If things go south later on, you don't have to do a full rollback and lose all your work. You can roll back to a specific save point and just undo the changes made after that point.
Like an undo button within an undo button.
Exactly. It's super useful for those complex transactions where you might want to recover from a small error without having to start the whole thing over again.
Can we go back to that money transfer for a second? Where would a SAVEPOINT be useful there?
Okay, so let's say after the $100 is successfully transferred, you want to update a log file to record the transaction, and this is all still within the same transaction. If that logging fails, you probably don't want to undo the entire money transfer, right? You could set a save point right after the update commands that handle the transfer. Then, if the logging fails, you roll back to that save point and only undo the logging part while keeping the transfer intact.
Makes sense. So these commands, begin transaction, commit, rollback, and SAVEPOINT, they give us really fine-grained control over how we change the database, right?
They do. They let you group changes, apply them, and even undo them if necessary. It's about having control over the flow of data.
Now let's talk about what happens when a whole bunch of people try to use the database at the same time. It's got to be tough to keep things from getting all messed up. I know the sources mentioned concurrency control. Can you explain why that's so important?
Okay, think about buying tickets for a concert online. Imagine thousands of people trying to see what seats are left and buy them at the same time. Without concurrency control, you could have two people trying to buy the same ticket at the exact same moment. Chaos. Someone could end up paying for a ticket that doesn't exist anymore, or the system could get all confused about how many tickets are actually sold.
Oh, yeah, that makes sense.
Concurrency control is a set of techniques databases use to manage these simultaneous operations without screwing up the data.
And one of the techniques they mention is locks. What exactly are they locking, and how does that help?
Locks basically restrict access to parts of the database. If a transaction needs to work with a specific piece of data, like a row in a table, it can request a lock on that data. The source mentions two types: shared locks and exclusive locks. A shared lock is like several people reading the same book, no problem. But if you need to write in the book, you need an exclusive lock so no one else can mess with it while you're working.
It's like a do not disturb sign for data.
Yeah, exactly. It prevents those situations where two people are trying to edit the same thing at the same time and end up overwriting each other's changes.
Okay, and then there are these isolation levels. How do they relate to locks?
Isolation levels control how much one transaction can see the changes being made by other transactions that are happening at the same time. They basically set the boundaries for how much peeking is allowed.
Peeking.
Yeah, like, can one transaction see the unfinished work of another?
Ah.
And there's a trade-off here. Higher isolation levels mean stricter rules, but sometimes that can slow things down because transactions have to wait for each other more often.
It's all about finding the right balance, huh?
Yeah, exactly. You want consistency, but you don't want the system to grind to a halt.
The source mentions a few different isolation levels. Can you quickly explain those?
Sure. So we have read uncommitted, read committed, repeatable read, and serializable. Read uncommitted is like the Wild West. A transaction can see changes made by others, even if those changes haven't been saved yet. This can lead to what we call a dirty read, seeing data that might later be rolled back. Read committed is a bit more cautious. A transaction only sees changes that have been saved by other transactions. Repeatable read ensures that if a transaction reads the same data multiple times, it'll always get the same value, even if other transactions make changes in between. And then there's serializable, which is the most strict. It makes sure that concurrent transactions act as if they're happening one after the other in a perfectly ordered line.
Wow, so many options. How do you choose the right one?
Well, it depends on your application. If you're dealing with super sensitive stuff like financial transactions, you probably want the highest level of isolation, even if it means things are a bit slower. But for things where a little bit of inconsistency won't cause a major problem, a lower isolation level can keep things moving quickly.
Makes sense. It seems like that command, set transaction isolation level read committed, is how you actually tell the database which level you want.
Yep, exactly. You're in control.
It's cool how we can influence those details.
Yeah.
Okay, the sources use a banking database as an example. How do all these ideas about transactions and concurrency control work together in that kind of setting?
Banking is a great example because, well, you can imagine how important it is for financial data to be accurate. The example they give, transferring funds between accounts, shows how that all-or-nothing rule is essential. If any part of that transfer fails, you need to roll back to make sure the accounts stay balanced.
It's like a safety net.
Yeah, exactly. Now, imagine a busy bank with tons of customers making transactions, checking balances, and depositing money all at the same time. Concurrency control with logs and those isolation levels we talked about ensures that no one's data gets messed up in the process.
It's pretty amazing when you think about it.
It is.
The sources have a section that's like a pop quiz with a bunch of key questions. Let's go through those just to make sure we've got everything straight. Okay, first question. What is a transaction and why is it important?
A transaction is a group of database operations that are treated as a single unit of work. It's important because it ensures data integrity. Either all the operations in a transaction succeed or they all fail. That's the key to keeping the data accurate and consistent.
Okay, and what are those ACID properties again?
Right, so quickly, atomicity means all or nothing. Consistency means the database starts and ends in a valid state. Isolation means transactions don't mess with each other. Durability means committed changes are permanent.
Okay, good. How do you start and finish a transaction?
You start with begin transaction, and you finish with commit to make the changes permanent.
What if something goes wrong during the transaction?
You use rollback to undo everything and get back to the starting point.
And what about those save points we talked about?
Those are like checkpoints within a transaction. You create one with save point name, and you can undo back to that point with rollback to save point name.
All right, now let's talk about multiple users. What's concurrency control and why is it so important?
Concurrency control is all about letting many users interact with a database at the same time without messing things up. It's like having a traffic cop at a busy intersection, making sure everyone gets where they need to go without crashing into each other.
Makes sense. What are the main types of locks used in concurrency control?
We have shared locks, which are for reading data, and exclusive locks, which are for changing data. Shared locks let many transactions read the same data at the same time, while exclusive locks ensure that only one transaction can modify the data at a time.
So it's about making sure everyone plays nicely together. What about isolation levels? What are they all about?
Isolation levels determine how much one transaction can be affected by changes made by other concurrent transactions. It's like choosing how much soundproofing you want in your apartment. You can completely block out your neighbor's noise or let a little bit in.
I like that analogy. What's a dirty read?
A dirty read happens when a transaction sees data that has been changed by another transaction but hasn't been committed yet. It's like reading a draft of a document that hasn't been finalized. The information might not be accurate.
And how do we set the isolation level for our transactions?
We use the set transaction isolation level command, followed by the desired level, such as read committed.
Okay, what's the key difference between read committed and repeatable read?
Read committed prevents dirty reads, so you only see data that has been saved and is considered valid. Repeatable read goes a step further and makes sure that if you read the same data multiple times within a transaction, you'll always see the same value, even if other transactions make changes in between.
Gotcha. What about deadlocks? Those sound scary.
A deadlock happens when two or more transactions are stuck waiting for each other to release the resources they need. Imagine two people standing in a doorway, each refusing to move so the other can pass. To avoid deadlocks, it's important to make sure transactions acquire locks in a consistent order, like always locking record A before record B.
So it's all about being organized and predictable. What should you do if there's an error during a transaction?
You should use rollback to undo the changes and bring the database back to a stable state. It's like hitting the undo button to erase any mistakes.
Okay, last one. What's the purpose of commit?
Commit is the command that permanently saves all the changes made during the transaction. It's like hitting the save button on a document.
Okay, that quiz was helpful. Now let's look at those scenario-based questions the source provided. First one, how would you write the SQL code to transfer funds between two accounts using a transaction?
All right, here's how you would do it. Let's go in transaction, update accounts, set balance of balance 100 where accounted to 1. Update account set balance equals balance 100 where accounted equal 2. Commit. This ensures that both accounts are updated correctly or that no changes are made if there's an error.
And the second scenario is, how would you handle a situation where a transaction fails during the process?
If a transaction fails, you use rollback to undo the changes. For instance, end, begin transaction. Update accounts, set balance. Balance 100 where accounted is 1. Uh-oh, an error happened here. Rollback. This would revert the first account's balance back to its original value as if the transaction never started.
It's all about being prepared for those uh-oh moments.
Exactly.
Well, this has been a really thorough exploration of transactions and concurrency control. We've covered a lot of ground, from the basic all-or-nothing idea to managing those transactions with specific commands, and then we dove into how these systems handle lots of users at the same time without causing chaos. It's clear that these are crucial concepts for anyone working with databases.
Yeah, it's all about ensuring that the data we rely on is accurate and trustworthy, even in complex and demanding environments.
And it makes you realize that these things are happening behind the scenes in so many of the applications we use every day, right?
Yes, absolutely.
Think about online banking, collaborative document editing, even social media. Transactions and concurrency control are working tirelessly in the background to make sure everything works seamlessly and our data is protected.
It really is amazing.
I think it gives you a new appreciation for the complexity and the robustness of these systems that we often take for granted. So next time you're doing something online, Take a moment to consider all the intricate processes happening behind the scenes to keep things running smoothly and to protect your data. It's a whole hidden world that's worth appreciating.
It is.